Okay. So in dissolution DNP, we're concerned with the problem of sensitivity. So we want to increase the sensitivity in magnetic resonance, which was a subject of research and development for decades, right? So people have developed cryoprobes that cost close to $1 million to increase the sensitivity by a factor 2 or 3. People have invested millions to have ultra-high field magnets, of course, for high resolution, but also for sensitivity. And sometimes it's only for sensitivity that we go higher in field. And we invest millions for a factor 1.5 or 2, which sounds crazy, but it's very important for many problems where we want to observe something that is in low concentrations. And it's really critical, this question of sensitivity. So this is the kind of investment we do for a factor 2 in sensitivity. Now, about 20 years ago now, it's in 2003, was invented the method called now dissolution DNP by the group of Klaas Goldman in Malmö, with at that time, I think, Jannin Larsen, who was a postdoc, and they showed that you can increase sensitivity by not a factor 2 or 3, but by a factor 10,000 or so, and then record super high sensitive spectra of low concentrated nuclear spins. In this case, it was 30 millimolar urea at natural abundance. So this is the thermal signal on the same sample, 65 hours, and this is one scan with dissolution DNP. And so right after the dissolution DNP was invented, there was a patent by this company called Nicomed that was immediately bought by another company called Amersham. And then GE came and bought the company. And they started to work on that. And it took them about 15 years to come up with a clinical system, but they did it. And they found a very nice application. And 99% of the groups have been working on these applications. And this application is metabolic imaging. So the principle is to take a small molecule like pyruvate, which is a metabolite, and polarize it, like Jan-Henrik Larsen has done, and then to take this molecule and inject it into a human. And what they could see is that because the molecule has such a high signal-to-noise ratio, when you inject it, you can first follow the biodistribution of the molecule. So you have no background, you can see where the molecule is. Plus, you can do localized spectroscopy. So you have information about localization, but you can also do NMR in the MRI machine. And you can see not only the molecule that you inject, so in this case pyruvate, but you can also see if it gets transformed into another molecule, in this case lactate. And so by doing localized spectroscopy at different positions, you can see, as a function of time, the signal of the pyruvate, and in this case of the lactate that comes from the metabolism of pyruvate into lactate by the cells. Okay, and what they discovered is that in cancer cells you have a super high uptake of pyruvate. So cancer cells tend to eat a lot of pyruvate, and they transform it into lactate at a high rate. So this is in a prostate cancer region, whereas in a healthy tissue you have very little uptake of pyruvate and no observable lactate production. Okay, so this is really the killer application. Most of the publications are around this. Of course, you have other molecules, other organs that are targeted, but this is really the killer application that has driven the field for 20 years. All the money comes from here. They say that GE has invested more than a milliard, so that's a billion, no, a million, a billion, a trillion, I don't know. It's really a lot of money for the clinical trials. And so now they're in phase 3 of clinical trials. They have done this on, I don't know, tens of humans. I don't know if it's 30 or more. They have about 25 sites that are now equipped with the polarizer that they use to do that. And it's not clear if this will go into the clinic or not, because it's very expensive, because it's very complicated. We don't know. Maybe in 5 years or 10 years, it will be in every hospital, or maybe it will just disappear. I don't know. But it's very impressive. What is very impressive about this is that what is used today is radioactive glucose. So if you have a cancer and we want to see if, how it evolves, we inject radioactive glucose, and then we do some position emission tomography, which works well. So the cancer will absorb a lot of the glucose, so you can localize the tumor, but it's radioactive. So before you take the bus, you have to wait an hour not to irradiate all the people around you, and you cannot do it many times. Otherwise, you end up killing the patient. So you can only do it once per week, I don't know. So that's a good thing. With pyruvate, it's not radioactive. You can do it many times so they can make more money. And you can do it on pregnant women, on child. You don't have the same safety issue than radioactive tracers. Another thing that is really, really impressive is that what you observe here is not the presence of the tumor. It's the metabolism of the cells in real time. Okay? So for example, when you do glucose, if you have muscle activity, then the muscle eat glucose and you have some false positive. Whereas here you don't have false positive because the metabolism of the tumor is different from the metabolism of the healthy tissue. Okay? That's one thing. And the last thing, which is really exciting for the medical doctors, is that if you give a medication to the patient, it takes sometimes a week or a month or 6 months for the tumor to evolve. Okay, so you don't know if the treatment works. You have to wait for a morphological change. And so if the treatment is not good, it takes weeks to adapt the treatment, and by that time, things have gotten worse. Whereas here, after a few hours or maybe a day, even though the tumor has not changed in shape, you see a change in metabolism. Okay? So you can see very rapidly if the treatment is working or not. So you can change the treatment to see if the cells are responding to the treatment. Okay. So that's it with MRI. Obviously, we are an NMR lab. We don't do MRI, but I had to talk about this application, which is super important. And now we'll switch to some other application. I don't want to give you a super broad overview of applications. I just want to give you a very few to give you a flavor of what we can do with dissolution DNP. Okay. So the first application I want to talk about, and again, I'm super biased because I'm just talking about some application that I know and that I like, is metabolomics. I put the picture here of Patrick Giraudot in Nantes, who is working on using dissolution DNP to study metabolomics. We started this project together a few years ago, and we've shown that you could hyperpolarize very complex mixtures. So you can polarize, for example, cancer cell extracts or plants or urine or blood. I mean, many samples that contain small molecules, small metabolites can be hyperpolarized. And you can increase the sensitivity, and you can do that with the current hardware with a reasonable repeatability of a few percent. So with this kind of repeatability, you can start to do metabolomics. You can start to see variations between different samples. I give you a list of papers, and during all the course, the papers that I put, they have a link. And if you have the PDF, you can click on the link and you can directly download the papers. You can go directly on the website of the publisher. So this is the first application I wanted to mention. I wanted to mention also drug discovery. This is a very active field of research in Texas, in the lab of Christian Hilty, and in other labs also. With dissolution DNP, we can enhance ligands that binds to protein, and that allows one to answer many questions. Does the ligand bind by many different kind of measurements? So if you have a mixture of ligands, you can find which one binds. And where does it bind? You can also look at the protein, because the polarization of the ligand is transferred to some extent to some parts of the protein. Or you can polarize water and indirectly transfer polarization from the hyperpolarized water to the mixture of protein and ligands. And there, again, you get some hyperpolarization of the ligand and of the protein. This idea to hyperpolarize water has been picked up by several groups, and I will come back to it later. You can use dissolution DNP to look at chemical reactions, and this is used, for example, to study polymerization or other chemical reaction like decarboxylation. So you polarize one molecules that will react with other molecules, and then you can see the whole reaction. What is interesting is that you have so much signal that if you have short-lived intermediates, in principle, you can see them with high sensitivity, whereas without hyperpolarization, you may need minutes or hours to see the intermediates. And it could not be possible because they don't live long enough. Whereas with dissolution DNP, you can see, for example, in this case, you see many intermediates. The drawback is that the hyperpolarization is not there for ages. So after a few tens of seconds or a minute, it just goes away. So you have a time window to look at your reaction. Again, I put you a lot of papers by the group of Hilti mainly, studying this topic. And now I go back to the water hyperpolarization. So this is a topic that started at EPFL with Quentin, actually, who is here. We used it for water LogZ drug discovery experiments, and we noticed at that time that the protein would also get hyperpolarized. And so we did a collaboration with Jeffrey at that time, and there was Dennis Kurzbach, who then started to work on that actively. Lucio Friedman also in the Weizmann Institute. And by combining hyperpolarized water with protein NMR, you can do fast sequence such as the SOFAST and record 2D spectra of proteins that are then hyperpolarized. Again, I added a list of papers. If you're interested in, you can have a look at all these papers that deal with protein hyperpolarization with water. Lucio was the first to do it. It was on amino acid, I think. Yeah, you're right. It was not proteins. I think it was small amino acids at that time, and yeah. A last topic that is becoming of increased interest is mixture analysis. So you have complex mixtures and you want to analyze them, and you can of course hyperpolarize these mixtures, but then if you do that, in order to really resolve the different species, you have to do 2D. And 2D is complicated with dissolution DNP because the hyperpolarization doesn't last super long. So what Lucio Friedman is working on, and also Jean-Nicolas Dumez, is to implement ultra-fast 2D NMR. And this is, for example, an example by Jean-Nicolas of ultra-fast DOSI, where you can resolve mixtures in a single scan on a hyperpolarized mixture. Okay. We did that also with Patrick Giraudot on cancer cell extracts. Of course, it's super nice, but you lose sensitivity. You lose, typically when you do an ultra-fast, you lose a factor 10 on resolution and 10 on sensitivity compared to a normal 2D. So you gain a factor 10,000 with dissolution DNP, but you lose then a factor 100 with the ultra-fast. So that's about it for. Yes, Diana.
In the early stage of dissolution, for instance, phosphate classes. So this is also working, for instance, for measuring phosphorus or like inorganic materials in general.
Yes. So Diana's question was of glass. Yeah. So you would have to polarize the glass and then apply some chemical corrosion and see in real time what's happening during the corrosion. Yeah, why not? You could hyperpolarize particles of glass, microparticles, and then mix them with a medium that will attack the glass and see in real time what's happening. We did a bit the opposite with Brad Schmelka. It was on like a generation of we polarize inorganic phosphate, and then we would see like particles shape forming. And this is not published, but there is a work by I don't remember his name, in Paris, who studied I think with carbonates how you can make particles. You hypopolarize carbonate, and then you form some calcium. Was it calcium carbonate, or I don't remember exactly. So you can start with the small molecule and see how you create particles. That has been done, but what you're telling is the contrary. So polarize the particle, and that, I think it has never been done, but if you can polarize the particle, then why not? Actually, particles, they have an advantage over small molecules is that they usually have a long T1. So, yeah. Any question in the remote? No. Okay, so let's move on. Okay, so we're interested in dissolution DNP to look at small molecules mainly in small quantity. So say you have, for example, 0.1 milligram of compound, such as pyruvate, because that's the #1 molecule in dissolution DNP. That's let's say it's labeled in the C1, so that's you want to look at carbon and it's labeled. We take 70 microgram. We put that in a NMR tube with 500 microliter D2O, and we measure that on a 300 megahertz spectrometer overnight on a labeled pyruvate. This is the kind of signal we get after 128 scans every 5 minutes, because the T1 is about 1 minute. This is the kind of SNR we get. Now, of course, if you want to look at non-labeled compounds, so if you look at the methyl or the other carbon of this pyruvate molecule, which is not labeled on the same amount, after one night, you don't get signal on a 300 megahertz spectrometer. And if you want to have the same sensitivity that you had on the labeled compound, you need 12 hours times 100 times 100, and that's already 13 years. So you're in big trouble. There are many reasons for the low sensitivity, which have been the subject of research for decades. So people have tried to go to higher field, to increase the electronics of the detection, the console, the NMR probe, making the probe cryo to bring down the noise of the electronics. So there are many, many ways we can improve this incrementally by a factor 2 or 3, which has been done. But there is a main reason for the low sensitivity, which is the low nuclear spin polarization in typical field and temperature conditions of NMR. Okay, so your sample is made of several nuclear spins, like 10 to the 20, 10 to the 23 nuclear spins, and these nuclear spins altogether create a global bulk magnetization, which can be described by this formula, which is proportional to the n number of spins, but also to the polarization. So the more polarization, the more magnetization you get. And then when you do the NMR experiment, you induce transition in your spin system, you excite coherences, or in a classical view, you bring the magnetization in the XY plane, and then you measure a signal that is actually proportional to this polarization, okay? So if we can increase the polarization, we increase the signal in a linear fashion, okay? If you increase the polarization by 10,000 fold, you get 10,000 times more signal. So that's the main message. The signal is proportional to the polarization. And the problem we have with polarization is due to this guy, to Boltzmann. So often in NMR, we describe the spin system by product operators. And here you see the density matrix for a thermal equilibrium one spin system, 1/2. Usually it's written like this. You have IZ plus half of the identity. And usually it's noted like this. So you have a huge excess of spin on one level and a huge depletion of spins on the other level. And that's what you see in the books. But in reality, the real situation is the following. So you have a polarization factor in front of your IZ operator. And in reality, this polarization is very small. So when you look at the distribution of population on the energy levels, you have almost as many spin up as spin down. And you have only a very small excess of spin up with respect to the spin downs. And when you measure your signal, you induce a coherence, and most of the spins give rise to no signal because they give some destructive interference. You have as many spin up as spin down. And so many of the spins are silent because they cancel each other's. And it's only the small excess of population on one level with respect to the other that gives rise to the signal, which is very, very small. And in dNP, what we're going to do during this lesson, during this training, is try to bring all the spins on the same energy level, okay, so that we have a maximized polarization, and so that when we pulse and we create the coherence, we create a large signal. But the starting point is the Boltzmann equilibrium. So we have, as I said, almost as many spin up than spin down. And this can be described by this exponential law, the distribution of population, exponential the minus h bar omega over kt. And so with that, you can calculate your polarization, which is the difference of population divided by the sum. And for a spin 1/2, this is equal to the hyperbolic tangent of h bar omega over 2kt. And we're stuck with Boltzmann for now. And if we look at the Boltzmann polarization at room temperature in a field of 7 Tesla, for C13, it's a few ppm, 610 to the minus 6. So this means that if you have 1 million spins in your sample, you only have a 6 spin excess on one level. So you only have 6 spins that actively participate to the signal. It's not really correct, but that's one way to see it. It's as if you had only 6 spins that were polarized, whereas you have 1 million spin. So to increase the polarization, we can act on the field, h bar omega. But we rapidly see that if you want a polarization close to 100% to unity, you need a megatesla, which is not practical. Or you can act on the temperature, and if you want to maximize the polarization, you need to decrease temperature in the millikelvin range, which is again not practical. It's really hard to cool down a lot of sample to millikelvin. It takes a long time. Plus, if you do that, the spins will not relax to thermal equilibrium because at millikelvin temperature, there's no phonons anymore to make the spins relax. So it will take years for the spin to relax to the thermal state. So we have to get rid of the Boltzmann equilibrium, and one way to do it is to rely on Albert Overhauser's idea, which is to use the electron gamma, which is much higher than the nuclear spin gamma, and therefore has a higher polarization. So the electron is much highly polarized in the same condition, and then transfer this polarization to the nuclear spin. So the first paper presenting this idea was published in 1953 by Albert Overhauser, and I just copied the conclusion here. The possibility of producing large amount of polarization by this technique is of great experimental interest. But the main problem that he had here is about microwave penetration, okay? Because he was trying to do that at higher field, and the microwave would not penetrate in the sample. Why? Because the sample he had was lithium, it was metal. He was trying to use the conduction electron of lithium, and it didn't work because the microwave would not penetrate in the metal. And this was in 53 in Urbana-Champaign. And next door, there was another guy called Charlie Slichter, who published the same year the exact same experiment that was proposed by Overhauser on the exact same material, but he went down to 50 kilohertz. So he went very low in field. There, the microwaves were not microwaves anymore. It was almost audio waves. It could penetrate, and you could get some descent enhancement on the lithium nuclei. via the transfer of polarization from the conduction electron of the lithium. So the magnetic field was what? 0.2 Gauss. Is that possible? And they got an enhancement of 100. So that was the beginning of DNP. There was a period during the 50s, 60s, 70s where DNP was applied a lot for high energy physics, for particle targets experiment in Saclay, in Berkeley, and also in CERN. So if you look at the literature that I'm going to show you through the course, sometimes there are some very old papers from that time, and they are really very, very nice papers. With, I mean, most of the methods that we use today, was the same in the 70s and 80s, just that we have better equipment, but it was all developed there. It's still active today. There are some experiments, for example, at the Tolchard Institute or at the CERN, where they use DNP the same way we use it in dissolution DNP, so low temperature DNP, to do high energy physics, to polarize targets for, I don't know, neutron scattering experiments or other experiments that I don't understand anything about, like quarks and gluons, etc. So this is still an active field. Low temperature DNP, same as the dissolution DNP, to polarize targets for high energy physics. But that's not our business. What we're concerned in is how to polarize small molecules. And I just want to show you an example. So this is the typical result we get here. So on the same molecule I showed you before, the pyruvate, this is a liquid state hyperpolarized spectrum of pyruvate after dissolution. We get typically this kind of signal without noise. Signal increased by 10 to 50,000, depending on what field you measure. And you get really high SNR. Now you can make the same calculation as I did before. If you want to measure this exact same signal on the exact same sample without dissolution DNP, you need to average for 50,000 times square, which is not a short amount of time. It amounts to 27,000 years. Okay. It doesn't really make sense, but it's just to give you a comparison that the things that we can observe with dissolution DNP could never be observed without. Okay. So here's a little video that shows the whole process. So you take a sample in which you have put some radicals and some glassing agent, we'll talk about it. And then we put that in the sample cup that we load in the polarizer that you will work on next week. And we immediately bring down the sample to the center of the magnet in the cryostat in the liquid helium bath. So the sample goes from 300 Kelvin to 4 Kelvin and then 1 Kelvin. And once the sample is in, we can bring down the pressure of the cryostat to the desired pressure, the desired temperature, and switch on the microwaves. And when you switch on microwave, you see immediately the signal that builds up. It takes a few minutes for protons. And then once we have achieved the level of polarization that we want, we bring in a dissolution stick that we connect to a transfer line, and we're going to connect this to the sample and spray some hot water on the sample and push the sample out. So the sample is very rapidly transformed into a liquid. It's transferred through a magnetic tunnel and injected into the NMR spectrometer in about 1 to 2 seconds. So we have some valves, some pumps to help boost the speed of transfer. And then so this is the valve, this is the little injector. So the sample goes at the bottom here. You see it's injected and it's stabilized in about a second. And then we can immediately trigger the NMR spectrometer and measure the hyperpolarized spectrum. This is when everything works. It seems very simple, but it's very complicated. So the sample is usually made of a molecule of interest or mixtures of molecules of interest or particles. impregnated particles, it can also be. To that, we add some solvents, usually also a glassing agent like glycerol or ethanol or DMSO, and some free radicals. And so we're going to talk about that on Wednesday morning, how to prepare the sample. One test that we make from time to time is to check that when we freeze the sample, so we put a drop in liquid nitrogen, we check that it's transparent, that it forms a little bead of a glassy bead. And this is a very nice test because when it's glassy, when it's transparent, it usually means that the radicals are nicely distributed. Whereas if it becomes milky, it means that it has crystallized, and when it crystallizes, usually the radicals get purified at the boundary of the microcrystals and DNP gets worst. So here you see we have a milky bead that doesn't polarize well and a glassy bead that in principle polarize well. So we don't do that every time. We do that from time to time to check that the sample formulation is okay. So next Wednesday, we'll go through all the sample formulation together, the different kind of sample formulation in the solution.
Can I ask something?
Yes, please.
Just about the milky and the other one. So what is the difference? Why do you obtain a better sample? Is because you put more of the glass or more of the radical?
So your question is why is it glassy? How did we manage to make it glassy?
Why one is better than the other one? Why
yeah.
the glassy is more?
So
because the formulation is different.
I think the milky one is just water and maybe some molecules plus radicals, but doesn't have any glassing agent. Okay. And the glassy one had some glycerol, 50% or 60% glycerol to form a glass.
Okay.
Sorry?
I say okay.
Does it answer your question?
Yeah, thank you.
Yeah. Okay, so we'll talk about that, a different glassing agent on Wednesday. And then with Charlotte, you will have a little workshop where you will prepare your own samples with different glassing agent, different quantity. You will check that. So in our sample, the most important is that you have your polarizing agents. You will see there are mainly some free radical molecules. And you have your target nuclear spins, for example, C13, on your molecules of interest. And we mix that together with a solvent, for example, water glycerol, so that it becomes glassy when we freeze. In our case, we will talk a lot about tempo. It's a nitroxide radical, tempol or tempo, and it's usually at 10 to 50, sometimes a bit more millimolar. So it's quite low concentration compared to the molecule of interest that can be up to several molars. And this is then put in our system at 1 Kelvin, and in our case, it's 7 Tesla. And we try to go in conditions where the electron polarization is close to 100%. For example, at 1.2 Kelvin and 7 Tesla, in our case, the electron polarization is 99.97 or 96%, something like that. So it's very close to 100%. And this happens really fast because the electron relaxation is a few tens of milliseconds. So when you put your sample, your electron gets polarized, and then you can do your DNP immediately after you put your sample. You shine microwave, and you transfer polarization from the electron to the nuclear spins. That's the DNP part. And so on the tomorrow morning and this afternoon, we'll talk extensively about the mechanism that are hidden behind this process of transfer of polarization. So that's going to be the subject of a bit this afternoon and tomorrow morning. Once you stop the DNP, you still have the electrons that are nearby, and we start to have the anti-DNP effect, which is if you stop the microwave, the polarization goes down again. You have relaxation. So you lose your polarization through paramagnetic relaxation. And that happens in the solid state, but also in the liquid state. So the trick of dissolution DNP is to melt the sample rapidly before the polarization goes away, but also to dilute the sample. So we have a sample of, for example, 100 microliter, and we will dilute it in several milliliters so that the radical concentration decreases a lot and the paramagnetic relaxation becomes insignificant. So we melt, but at the same time we dilute so that the paramagnetic relaxation vanishes, and that way we can have hyperpolarized molecule in the liquid state that stays for tens of seconds or more. Yes? There's a question?
It'd be more interesting to put, I don't know, like precipitate somehow the radicals to get not the dissolution.
Yes.
Okay.
Yeah, that's a very good idea, to precipitate the radical. That would help to have less dilution. Yes. So there are some people working on that. How to precipitate the radical. In our case, we want to separate the radical by attaching the radical on matrices, on solid matrices. Some other people are working on UV excited radicals. So these are radicals that when you heat up, they just disappear. They recombine. But not anybody yet has done an experiment of dissolution DNP, so melting and transfer without dilution. We always need some dilution, at least to heat up. I mean, the best way to melt is to bring some hot water on the sample. That's the best way we found till now. Some people have tried to do in situ melt, like with a laser or with a hot copper, and this works to some extent. And but this problem of melting and diluting is very critical in dissolution DNP, because you get 50K enhancement, but then you lose a factor 10, 50, sometimes 100 in dilution. Well, what the patent says is that you have to dissolve the sample while it is in the polarizer, while it is in the field of the polarizer. If you try to remove the sample and melt it outside, it doesn't work. Well, in fact, it can work in some conditions, but it's really difficult. So you have, in the initial form of the experiment, to dissolve while it is inside of the polarizer. Okay, so once it's polarized, you will melt and transfer the sample to the NMR spectrometer. Okay, so let's have a break now, and then we'll finish this section and move on to the DNP mechanism section.